an AI-generated post for your viewing pleasure. Forget complex deep learning models. The secret to navigating even the most challenging mazes may lie in the humble Braitenberg vehicle. A new study shows how genetic programming can uncover surprisingly simple yet effective navigation strategies, upending the assumption that high-dimensional, partially observable tasks require sophisticated artificial intelligence. Navigating through a complex labyrinth with dozens of rooms and corridors might seem like a task that would require advanced deep learning algorithms capable of processing intricate visual information and maintaining an internal representation of the environment. However, a team of researchers has uncovered a surprising alternative. By employing a genetic programming approach called Tangled Program Graphs, they were able to evolve agents that exhibit Braitenberg-style behaviors to successfully tackle the challenge. The My Way Home scenario in the ViZDoom environment presents a formidable test of an agent's navigational abilities. With a first-person visual perspective and sparse rewards, the task requires the agent to find its way through a maze-like structure to a specific goal location. While deep reinforcement learning methods have been applied to this problem, the researchers hypothesized that the constraints of the Tangled Program Graphs framework might lead to the discovery of simpler, yet effective, heuristic-based solutions. At the heart of the Tangled Program Graphs approach is the idea of evolving modular, reactive behaviors from a limited set of basic instructions, rather than relying on more complex deep learning architectures. The researchers limited the Tangled Program Graphs agents to a simple arithmetic instruction set, eschewing sophisticated image processing operators or memory mechanisms. This bias toward simplicity, combined with Tangled Program Graphs' ability to discover emergent behaviors through the interaction of multiple programs, proved to be a winning formula. The results were striking. While a standard deep Q-network agent struggled to navigate the labyrinth, the Tangled Program Graphs agents exhibited a clear mastery of the task, consistently reaching the goal location. Analysis of the champion Tangled Program Graphs agent revealed the source of this success: a set of Braitenberg-like heuristics, including wall following, reorientation, and pathfinding behaviors, all emergent from the interactions of the agent's modular programs. Remarkably, these Braitenberg-style behaviors persisted even when the agents were tested in a simplified environment without a goal, suggesting that these navigation strategies were not just task-specific, but fundamental to the agent's decision-making process. The Tangled Program Graphs agents achieved this level of performance while indexing only a tiny fraction, less than 1%, of the overall state space, a testament to the efficiency of their evolved solutions. The findings of this study challenged the prevailing assumption that high-dimensional, partially observable tasks, like the My Way Home scenario, require sophisticated deep learning approaches. By embracing the constraints of the Tangled Program Graphs framework, the researchers have shown that simple heuristics can often outperform complex models, at least in the context of visual navigation. This work builds on a rich history of research into Braitenberg vehicles, which have long been used to model the emergent behaviors of biological organisms. However, unlike previous Braitenberg-inspired approaches, the Tangled Program Graphs agents discovered these navigation strategies entirely through evolutionary optimization, rather than having them pre-specified. The contrast between the Tangled Program Graphs agents' Braitenberg-like behaviors and the deep Q-network agents' more direct, goal-oriented approach highlights the different biases and strengths of these two paradigms of reinforcement learning. While deep learning excels at extracting complex representations from high-dimensional data, the Tangled Program Graphs approach appears to be more adept at discovering modular, interpretable, and potentially more transferable navigation strategies. As the researchers propose, future work could explore how different task geometries and environmental structures impact the complexity of the Braitenberg-style heuristics discovered by the Tangled Program Graphs approach. This could lead to a deeper understanding of the factors that influence the emergence of simple yet effective navigation strategies, with potential applications in robotics and other real-world domains. The study's findings demonstrate that the constraints of the Tangled Program Graphs framework can be a powerful ally in the quest for efficient, interpretable solutions to complex navigation tasks. By evolving Braitenberg-style behaviors, the Tangled Program Graphs agents were able to outperform a state-of-the-art deep reinforcement learning approach, navigating the intricate My Way Home labyrinth with a surprising degree of simplicity and elegance. This work challenges the notion that high-dimensional, partially observable environments necessarily require sophisticated artificial intelligence. Instead, it suggests that by embracing the right biases and constraints, we may be able to uncover navigation strategies that are both effective and remarkably straightforward. As the researchers explore the impact of different task geometries and environmental structures, the potential for these Braitenberg-inspired solutions to inform the design of robotic systems and other real-world applications becomes increasingly tantalizing. In an era dominated by the ever-increasing complexity of deep learning models, this study serves as a refreshing reminder that sometimes the simplest solutions can be the most powerful. By harnessing the power of genetic programming and the principles of Braitenberg vehicles, the researchers have opened up a new frontier in the quest for efficient and interpretable navigation strategies, with exciting implications for the future of autonomous systems and beyond.